So it's lecture number 7 going on, and we discussed last time the notch effect, notch sensitivity, and these parameters effect onto the von Mises stress. And this is information that you shall need in your project work. And learning target for today would be to comprehend something about fatigue. So now we are moving on to a topic of fatigue. Let's see if we have enough time of making calculations today. There's quite a bunch of information for today, so it might be that we don't get the chance to do calculations just today, but nevertheless try to memorize this lesson information during next week's before the next machine elements lesson, because this is something you will be going to be needing in your project work as well. This presentation is not yet in the Moodle because I don't know how far we can get in this topic in the slides, and after the lesson I will put the slides that we covered into Moodle, and the rest of it will continue after the winter vacation. But the main learning target today is to understand what is crack initiation and what is the crack growth process and metallurgical background in a fatigue fracture, and that you would recognize and understand different parameters that do affect, and that on the other hand side can be used in improving the fatigue strength in the design. You will learn something about fatigue related terminology, basic terminology, and you will learn the theoretical and empirical background of so-called SN curve, sometimes called as a Wöhler curve. And also you will maybe recognize methods of advanced fatigue assessments. Let's see if we have time to go into that. If not, we'll take it next time. So, what is fatigue? In the picture you can see a man who has been taken by fatigue. Fatigue is a term that is being used generally as describing tiring or tiredness. But when we speak in mechanical engineering, this fatigue term is used to describe a phenomena in which a component will exhibit a damage due to a cyclic, meaning alternating load. So varying load will cause a damage, and that is called fatigue. And this damage is on the contrary to the static breakage. This fatigue damage is progressive in nature. So it will take time and multiple cycles to reach the Roman, your mic is on. Can you mute it, please? And this term fatigue, it was first used by a French engineer and mathematician J.V. Poncelet in his book about mechanics 1839, and later used by I think British F. Braithwaite in the book on the fatigue and consequent fracture of metals. That was basically the first ever written record of fatigue in metals. And where it all started, it started when the industrialization era started in the 19th century, because use of metals, especially steel, increased dramatically, and also due to that, also the damages and failures due to the material breakage increased. There were quite a significant amount of railroad accidents all over 19th century. One of the most disastrous being the Versailles train accident on October 1842. And in quite a many of these cases, the reason was fatigue fracture. But there was no proper scientific knowledge about the topic at the time. There was some pseudoscientific theories, for example, that this fracture is caused by a crystallization due to magnetic field of Earth, and stuff like that. Pretty much could be said that it was nonsense. And these theories couldn't be used in a profound scientific investigation of the topic, until there came a engineer from Germany called August Wöhler, and he was a railroad engineer in Germany, and he was starting to investigate in profound manner why the shafts of a train did fail, even though the nominal stress was far below the yield strength of the material. So he was the first one who was investigating in a systemic way, a defined way, why this fracture would happen. And his investigations and numerous tests led into a fatigue life relationship that we later know as a Wöhler curve, or in the English speaking world we call it SN curve, stress life curve. Third is in the cyclic loading, which is from the crystal grain theory. And what is cyclic loading? Cyclic loading means that the load varies over time, and the variation of the load can be either systemic or arbitrary. Systemic defined variation is, for example, a sinusoidal bending moment fluctuation, like in rotating machinery. If you have a mass load on a shaft, which is constantly bending the shaft into downwards, and you rotate the shaft, that will cause that the shaft itself will bend in different directions due to the rotation. The load stays in the same direction, but not in relation to the shaft. And that will cause a sinusoidal bending load in the shaft. Another example could be, for example, constant frequency pulsating load in a packaging machine, or something else that is that we know what is the actuating frequency of the loading. This is of course fairly easy to put into the mathematical form. Therefore, this sinusoidal cyclic loading is by far the most important one, because we can calculate how many pulses and what is the amplitude, etc. A more difficult form is a arbitrary variation, which is, for example, natural loads. Natural variation loads like wind or wave loads, they typically are arbitrary variation loads. Or you could consider, for example, bumps on the road which hit the car suspension. That's also a variation, arbitrary variation load. In the lower right hand side picture you can see a history of cyclic loading of a wind turbine blade. So you can see that you cannot find there any systemic sinusoidal or any other variation. It's just arbitrary. What is important to understand about the loadings is that in the universe there is no such thing as a pure static loading. In essence, if we go into the most precise understanding of things, because all loads vary at least to some extent. Just that in engineering we tend to take very small or extremely slow variations as static. You might think that, for example, gravity of Earth would be static loading. Yeah, we can consider that way, but in essence also the gravity changes a bit over time, and it's different in the different regions of the world. But in true nature, all loads more or less are variating loads. Then some key definitions and characteristics in cyclic loading. The most important ones are the first two: stress amplitude and stress range. Amplitude it's fairly easy to understand when we look at the picture. Amplitude is the deviation from the mean value, so either to the top of the load or to the lowest valley of the load. And the stress range is then twice the amount of the stress amplitude, that is from the lowest valley to the highest top. And if we calculate this stress range from the maximum and minimum stresses, it's of course the maximum value minus the minimum value. Then important factor when we consider varying load is the number of cycles, so of the number of variations. And the one cycle is always one full reversal. So like in this picture, in the sinusoidal case of loading first half sinus form into the plus side, and then plus side on the mean stress, and then to the negative side of the mean stress, and then back to the zero. So one cycle considers both of these. Sometimes some people consider that it's only half of it, but no, it's one full reversal back and forth. And then mean stress is the value in between the peak and the valley, just in the between. That's fairly quite easy to understand. And these are, I would say, the most important definitions in the fatigue, which you would need to understand and use in the calculations. And what is important to note that these prefixes and subscripts, they are equally applicable to any load or stress definitions. For example, we can define delta T, then it's meaning torque range. It could be delta M, then it would be bending moment range, or we can define the von Mises stress amplitude, then we just write a small a in the subscript. And the mean bending moment, for example, M in the subscript. The same philosophy applies. Fairly simple and straightforward. Now when we go look into more detail about this cyclic loading and considering the minimum and maximum stresses, we can calculate so-called stress ratio using the minimum and maximum stress. Sigma min divided by sigma max is the stress ratio. And that is telling us what is the form of the cyclic loading. So the stress ratio, which is denoted as R, is often described in combination with, for example, fatigue results. If you look the scientific papers for fatigue results for certain materials, you often find that they state that R is maybe 0 or 0.1, or R is 1, R is minus 1. And that states what has been the stress ratio in the tests. Why it's important? It's important because it pretty much affects the results. Later on we can see how does it affect, but it has significant effect on the fatigue life depending what is the stress ratio. And there are three main cases which can be distinguished from each other. First one is this A, which is fully reversed loading. And that would mean that minimum stress is somewhere here below, so it's compression, and maximum stress is in the tension, and the mean stress is exactly at the zero, meaning that there's equal compression and equal tension in the variation. And this means that the mean stress in the center is zero. So the amplitude to the tension side and amplitude to the compression side are equal. And when we calculate the R ratio for this case, it of course results in R to R minus 1. Sigma minimum is compression minus, and sigma max is tension. It's positive, and when the numerical values are equal, it will result into 1 and in minus 1. That is the first case, and quite often this is one of the most severe cases of the loading, so that it's pulsating from tension to compression. Not always, but quite often. Then another option would be a case where we have this variation, sinusoidal curve, is shifted somewhat vertically, up or down, which would mean that we have now the mean stress somewhere else than in the exactly zero. It could be higher up, like in this picture B here, so that we have the mean stress in the positive side, meaning that the most part of the loading is acting on the tension side, and only small portion is on the compression side. And that means that the mean stress is also tensile mean stress. Or it could be that this, which is not picturized here, but it could be that this curve is below the zero, which means that the mean stress is on the compression side, and most of the time the loading is on the compression, only small portion is on the tension side. This is the second case. And the third case would be that we have a case where we have a zero to tension, so that we shift this cyclic curve in a way that the minimum stress is exactly at the zero, like we see here in this picture C. And this will result into stress ratio to be zero, because the sigma minimum would be zero, therefore R is also zero. And this is another important case in a way that quite often components are fatigue tested with this kind of R0 or R nearly zero stress variation. Of course, there would be a fourth case also where the maximum stress would be at the zero and the minimum stress fully on the compression, but that is not that important. Of course, that is possible, but then it would be completely on the compression, and that is not as important case due to the factor that if we have only compression, it doesn't tend to cause fatigue failure. There are exceptions, of course, like welds, because there are residual stresses. But if we have a component which has no residual stresses, a situation where there be only compression, even pulsating compression, would not cause fatigue failure. Okay, here is the same thing. Same thing for case A in an own slide. Same thing for case B and case C. Okay, now we know the basics and the basic definitions behind the fatigue. And next one is to learn what is a Wöhler curve or Essen curve. Has anyone of you been maybe familiar with the Wöhler curve or Essen curve before? You can raise your hand or say yes or put it into a chat if you like. So I would know if you have some experience with it before. At least Tirkkonen, can you share how have you been using Wöhler curve before?
Well, I think we checked this out in our last course in a couple of times.
Give me mitoitus ja mallinnus.
Yes.
Yes, of course. You see it there.
Yes.
Sure. Okay.
But we didn't do any calculations or whatsoever.
Yes, okay. Because I think that most of you, at least the students from Lappeenranta, it's probably the first time you ever encounter this. So let's go a bit into the behind what is Wöhler curve. So the Wöhler curve is a empirical curve that describes the fatigue life, meaning the number of cycles, number of variations, as a function of the stress variation level, which is then the amplitude or range. So if we look at this previous picture, it defines how many cycles with a given stress variation the component can last until it breaks. Maybe some of you have been doing um, like bending a steel wire or maybe or bottle cap with your hands, and when you bend it multiple times, you will eventually break it. And the amount of the bends that is required to cut the wire or cut the cap of the bottle, that is the number to failure. But when we do a defined Wöhler curve or Eschen curve, we have to do multiple tests. So this curve is a result of many tests which need to be done for several defined stress variation level. And because the fatigue strength tends to be it's a random distribution variable. It's a scatter in the results. We have to do multiple tests with the same stress variation level also, at least 3, to gain at least some kind of statistical confidence with the results. And what is important is that we always keep the stress variation, the amplitude or range, same within the same set of components. For example, here we can start with this highest stress amplitude, like here, and the result would be 1, 2, 3, 4, 5 numbers to failure. So we can count how many cycles it requires to break the component. And because there's a variation in the components, variation in the microstructure of the material, etc., it's not the same result for all of the components. But we have 5 components and we get a scatter on the results. And when we make a statistical approach to these results, we can find that there's some kind of average in the center of these 5 results. That gives us first point of the curve. The curve is here, the red, of course. Then we need to perform another test with a different stress level, in this case lower level, like here. And again, we perform the 5 test specimens with the same stress variation level. And we tweak and bend it back and forth until all of them break. Some of them last a bit longer, some of them a bit less. But because the stress amplitude, the stress variation is lower than the first test set, they, of course, should last a bit longer on average. There could be some components in the first that might last even longer than the poorest in the second, but nevertheless, generally, the lower stress variation level gives us longer lifetime. That's understandable. And again, we can find a sort of center point of these 5 tests, and that gives us a second point for the curve. Now we have already 2 points, and we could already now start writing a curve between these and start to extrapolate where would be where we could see what could be the lifetime for different stress levels. But of course, 2 stress variation levels is not enough to gain enough of confidence. Then we perform third test, again 5 results, share somewhere the average. Again, new test with a lower level, again 5 results, a bit higher lifetime on average, and again and again and again. And in case of steel, we typically reach a point where below the specimens do not exhibit failure, which means that they would basically last more or less forever, the variation. And that would give us the key point in this curve, and that is called the fatigue limit. But now when we have these different stress levels here, we can write down a curve combining these averages of different set of specimens. And that is now the Wöhler curve. And the good side is that now when we have drawn this curve, we can take any stress variation level and refer that to the curve, and that will give us the lifetime of the component. We don't need to have a test exactly done with the same stress amplitude, because we have this curve and we can refer the amplitude to the curve, and that will give us the number of cycles to failure. And also what is important in this Wöhler curve that, as you can see, this is the x-axis is logarithmic, and quite often both axes are logarithmic, but almost always at least the x-axis is logarithmic. And the reason is that these differences between the lifetimes, meaning the number to failure, they are so big that if we would put this into a linear scale, it would be very difficult to read. So almost always it's described in a logarithmic scale, at least for the cycles, sometimes also with a stress amplitude, but at least for the cycles it's logarithmic.
I have a question. What is the distinction between cycles and I forgot the words on the previous slide, between one zero value and the second zero value? Yes. I think, yeah. Yeah, oh, it's still cycle. Okay, sorry. Just
yeah.
Confused it.
So number of cycles to failure is the lifetime. So sometimes I only use word lifetime, and that means the number of cycles to failure. So NF. Lifetime means the number of cycles. It's not necessarily time. It could be also time. If we have a certain constant frequency, we can also calculate what is the time behind the cycles of failure, like the rotation machinery. But usually that is not the important thing to know. What's important for us to know is how many cycles, and that is the lifetime. So if I sometimes speak about lifetime, it doesn't mean time in seconds or minutes or hours. It means the cycles to failure.
I basically started thinking about periods between the, not peaks, but between the zero values. So is it also applicable word for cycles?
Periods. Perhaps, I don't know, I'm not that good in English. I would say that is there some other meaning behind that could maybe change it into the ears of our English-speaking listener? Could be, I don't know. Just that I've never seen such word being used in this context.
Okay, thank you.
But if it helps you to understand, you're free to consider that way. But I wouldn't write it in a scientific paper.
There is no problem with understanding, luckily. It's just words.
Yeah. Sometimes the words are quite important because it sort of guides your thoughts into a certain direction. Okay. So, as mentioned, these multiple tests with the same stress levels are needed to gain the reliable results. And the reason to this is that the fatigue strength is a random variable. Of course, the static strength is also a random variable, but not even nearly to the same extent as a fatigue strength. If you take a tension rod or 5 pieces of tension rods and you break them with a tension until breakage, you will probably get some scatter in the results. And that's quite normal, but the scattering is nowhere nearly in the same extent as with the fatigue results. Because in the fatigue results, it could be that a certain component lasts for 100,000 cycles, another component lasts for 1 million cycles. So the variation is much bigger. And also something to know about this is that the distribution with the results in the fatigue, it's not usually normal distribution, but a distribution that fits better or seems to fit better to this result is so-called Birnbauer-Saunders distribution. So it's not symmetrical with the peak. It's slightly sloping onto the higher side of the stresses. And usually the tests are done for 0 to tension, R0, or fully reversed load, R-1. And what that means, that we will learn later on. Okay. Previously we spoke that this curve is in a logarithmic scale, at least in the x-axis. And here's the reason why. In this picture, you can see this Wöhler curve of a certain aluminum. First of all, it's here in the left side picture, it's described in a linear scale. So you can see that in the x-axis you have 10 million, 20 million, 30 million, 40 million cycles to failure, and there's the result. As you can see, the lifetimes for the larger amplitudes, close to 300, more than 200 megapascals, they are so short. The number of cycles to failure is so small that it's difficult to see it from the curve. But where we go into lower stress variation levels, they tend to be much higher numbers to failure, and the distance between the individual results is far bigger than it's in the starting phases of the tests. And therefore, of course, this is quite difficult to read, and that is the reason that we want to put it into a logarithmic scale, like we see in this right-hand side picture. Another important factor what comes to the Wöhler curve is that when you've done your physics laboratories, for example, you usually do it in a way, and when you make a graph out of it, you usually do it in a way that you have the independent variable is on the x-axis, and the dependent, which you are measuring, is in the y-axis. So the scattering is in the direction of y. This Wöhler curve goes in vice versa. So in the Wöhler curve, you can see that we have the defined variable, which is the stress level, that is defined for each test set, and the result, which is the scatter, it's on the x-axis. And the reason for this is that purely just that Mr. Wöhler decided this approach, and it has been used since. But if you look at the mathematics or physics in other fields, usually the dependent variable is written on the y-axis. It's just good to know that it's in the Wöhler curve, it's other way round than in the many other fields of engineering and science. Okay. And what is important and interesting and a happy thing for all engineers is that when we have a written curve, we can put it into a mathematical form. Everybody loves that we can put physics into mathematical form. Yippee yay. So when we have a Wöhler curve defined, we can write the equation. If we have it on a log linear scale, the equation as shown above, C plus D log to NF, where the C defines the constant that describes the Wöhler curve intersection to y-axis. The D is then the constant that describes the slope of the curve, and NF is of course the variable in the x-axis, number to failure. And if we put it into a linear scale, we can get it into a form like the below. So sigma A is equal to A times NF power B, where this B is now, small b is now the sloping factor, and the A is now the intersection point to y-axis. Same thing, just that it's in a different form. And previously we already spoke that there is a knee point in the Wöhler curve. Where was it, the picture? Here. At some point, you can see that this curve is going horizontal. That's called the fatigue limit. And it's important to know that this phenomena, it only applies to certain materials. Steel, titanium, for example. They have this tendency that when the stress level variation is low enough, the component lasts forever. So there's a certain point at which the lifetime starts to increase rapidly. And this is something we can utilize and is extensively utilized in the engineering. Because if we now design the component in a way that the variation of the stress will stay below this fatigue limit, there is no crack initiation, there's no fracture ever, theoretically. So theoretically it will provide infinite lifetime for the component. So this flat part of the Wöhler curve is the fatigue limit for the material. Jaakko has a question, go ahead.
Yeah, since we can define the curve or a point on the curve where we never break, or there will never be the crack initiation or the peak. Doesn't that also mean that if the load changes, the curve changes permanently? For example, when you calculate that a spring will last 100 years, but if the load changes significantly for, let's say, a five-year period of time, doesn't that alter the end also? So the material changes during the risen load, which causes the element to change and bend more, and then take more fatigue, and so on and so on.
Yes, of course. For example, if we design the spring, like in this picture, we have designed the spring in a way that the loading would be below 400. And that would give us more or less infinite lifetime. Now, and if we at some point increase the loading, the driver is driving too fast on the bumps, and the loading, the spring is then on the range of 500. That would of course mean that the spring has then a defined lifetime, which we can find from Wöhler curve over here.
Yeah, so it doesn't. It just takes the load of the 500 for a short period of time, which changes the behavior of the material with the 400 load.
That is a very good question, actually, and you are going a bit forward on that because later we can see equation where we can combine effects of different stress variation levels. That's called so-called bulk grain minor rule, where we can see that if we have different levels of loadings, some of them are here in the sloping part of the Wöhler curve, some of them may be below the fatigue limit, and how to combine that effect and how to calculate that. There is an equation for that. And of course there you can understand easily that the effect of the higher stresses is more significant even with the lower number of cycles, because they stress the component, they stress the spring more than the lower levels. You can have more low-level stress amplitudes than you could have cycles of higher stress, of course. But also there's a factor that affects to it, so that it could be that even though you only have a couple of high stress peaks, in some cases it causes that the crack initiates, and then after that also the lower level stresses will make the crack to grow. So therefore the high stress peaks, they are really harmful. They are actually more harmful.
This was the thing that I was wondering, that
yes.
those like singular high loads will have an effect on the material, so that it doesn't take the lower load.
Yeah, and it's even though they can, this couple of high stress loads, they are included in a Palmgren-Minor rule, it doesn't fully take the severeness into account in such, how would I say, enough, because really the high stress amplitudes, if they get the cracks to initiate, then you can have smaller amount of stress that will make the crack roll. For example, if you have a constant amplitude for 390 megapascals constantly, no bigger stress amplitudes at all, you could be fairly reliable that the component will last forever. But if you have, for example, 10 or 20 700 megapascal stress variation cycles in between, no more than 10 or 20, it could be that these higher stresses already cause the crack to initiate. And after that, it could be that even 300 megapascal stress variation will eventually get the crack to grow further. That's a good point.
Yeah, thanks. This answered my question. Well.
Okay. But what comes to fatigue limit, you must understand that it's a property that is depending on the material. So aluminum, it does not have fatigue limit. So Euler curve for aluminum will go straight down, or the sloping into down to the zero. It means that no matter how small the stress variation level is, for aluminum it will cause the fracture at some point eventually. Okay, it might take quite a long time, but nevertheless, eventually it will break. So from that point of view, a stainless steel a marine boat would be maybe better than the aluminum boat. If you want the boat to be surviving to your grandchildren.
But how about modern car bikes that are mostly made of aluminum? Does it mean that in like 50 years they're gonna have cracks and be damaged severely?
It's difficult to say if it's going to be 50 years, but eventually, yes, they will break. That's for sure.
If it's any consolation, modern airplanes use less and less aluminum by the model, so the amount of aluminum is quite low actually on modern airplanes. It's really those old ones that are mostly aluminum.
Could be so. I don't know that much about airplane engineering.
On another lecture, there was a teacher that we covered this part, so that there is like often an example on material selection that we need to select a material for an airplane, for example. But he said that it's more and more like carbon fiber and stuff like that that they make the planes out of.
The reason probably is that the carbon fiber, considering the strength and the stiffness, it's much lighter. I don't think that the main reason is that is the fatigue property of aluminum, because there is also fatigue properties for carbon fibers, and for those it's even more difficult to describe and assess. So carbon fiber or generally composite fatigue is much more complex than it's for homogeneous materials. But nevertheless, that's true that probably carbon fibers are coming to the passenger aircraft as well. They've been used in the military vehicles for quite some time. Okay. Then you probably saw that I was speaking both about stress amplitude and stress range while showing these pictures to you. And the reason is that in some topics we use stress range, not the amplitude. Okay, amplitude is used most often, but there are some fields of engineering, like welds, for which the stress range is used and not the amplitude. And why it's important to distinguish? The reason is that if you are applying, if you refer to stress amplitude to a certain Wöhler curve that is done for stress range, then you will basically have double too high stresses. So there's a serious risk of early damage. So that you must keep in mind, that you have to always look what is written in the y-axis. Does it refer to stress range, which is usually described by a large delta, capital delta, or does it refer to stress amplitude? But it's fairly easy to see, because it's most often it's written there, and then you just know which one is being used. Okay, then something about the metallurgical background of the crack. I spoke about crack initiation. And what is crack initiation? So if we look at pretty much any material, most construction materials are non-homogeneous. If we look at the microscope, we consider steel to be homogeneous, but in the microstructure level, it is not. It is comprising of so-called crystal grains. In the right-hand side picture, there's a microscope picture of pure iron, and there you can see that there are these grains which have certain boundaries, and it's the formation is more or less arbitrary. And this crystal grain structure is result of solidification process, and it's dependent on the alloying, what kind of alloys are in the molten metal, how it is being processed. For example, milling of the steel rods and sheets, they do affect to the crystal grain structure, and it can be benefited in the manufacturing process. And also, of course, heat treatments. If you do a quenching and tempering for the steel, that will change the crystal grain structure within the material, and we can utilize that to gain, for example, more harder grain structure than it originally would have been. But what is important about the fatigue in this crystal grain structure is that these grains, they have all, of course, these grain boundaries, and related to the stress, there's always some grain boundaries which are sort of unfavorable in relation to the stress that is in the material. And those grain boundaries or planes, which are the most unfavorable, they first develop so-called slip bands under load, which means that these materials start to slide, the grains start to slide with respect to each other, slightly, not much, very little, but nevertheless. And when the component is under cyclic, meaning varying load, it will cause numerous of these kind of slip bands which will occur within the stressed area. They are, of course, in a very, very small area of the component. And when we continue the varying load, they will further cause these kind of extrusions. So some portion of the material remains sort of extruded out from the original surface, and some of them remain protruded inside the material, considering the original surface. That is called intrusion. And from these extrusions and intrusions starts the fatigue crack. And when we have first, there will be numerous of these intrusions and extrusions, and when we further continue the cyclic loading, these some of these will grow further, and they will further join together, and then they will form into crack. And that is the birth of the crack, and that is what we call initiation. And I don't refer as a crack here as a drug. It's this in the material. And the thing that Jaakko asked is here that after the crack has been initiated, also a smaller load is then able to develop the crack further. So even when we have the crack available, after that also those loads that before crack wouldn't have caused the initiation, after the crack formation, these smaller loads will make the crack to grow. And the crack will always propagate, meaning propagation means growing of the crack. It's easiest in the direction that is perpendicular to the major normal stress. That is easy to understand. If you have a thin crack and you want to make the crack longer, you of course will pull these sides of the crack apart from each other. That is the most efficient way of trying to grow the crack further. Here in the picture is a couple of examples of different materials and how the crack shows. In the lower picture you can see right at the top of the black arrow, you can maybe see a thin black line, and that is the just recently initiated crack. Very small. The scale in this white bar is 2 micrometers. So the width of the crack it's really small. Okay, and now as we understand that this developing of the crack it requires less energy to develop the crack when we pull these sides of the crack apart. That is something we describe as mode 1 crack propagation, like shown here in the picture. Mode 1 is the case where we pull these sides apart, and that is the most efficient way of propagating the crack. And if our stress is in this, or the stress variation, load variation is in this direction, then the crack will propagate the fastest. Another possibility would be so-called mode 2, which is this kind of shearing or sliding mode, so that there's a shear plane between the which is dividing the crack. That requires more energy to make the crack grow. And the third one is the so-called tearing mode, which is you could say that it's kind of a shearing also, but it's in a different direction than the sliding mode. And this eventually also requires even more energy to grow the crack than the mode 2 or the mode 1. And this mode 1, it's important because it requires the less force, least energy to crack to grow. So therefore, the crack may initiate if the crystal grain structure is in such direction that the loading is only causing the crack for mode 2 or mode 3. It might be that crack has been initiated in mode 2 or mode 3, but eventually mode 2 and 3 tend to turn into mode 1, which means that the crack will reorient itself, that it is progressing in mode 1. And in this case, the crack growth direction is perpendicular to the major principal stress. And it's also possible that this crack direction will change within the structure. And that is often the case if we have, for example, changing loading in the construction, or we have residual stresses. The crack will always want to grow into the direction where it's easiest to grow. And depending on the surrounding stress conditions, it will find the direction where it's the easiest. And then these mode 2 and 3, as mentioned, they require more energy, and they will eventually, if the crack will be growing further, they will eventually reach mode 1. Okay, so here we have two pictures of fatigue fractured components. First, the top, we can see that we have had initiation of a round bar here in the bottom. That's the initiation phase. Then we've had some crack propagation, maybe to 25% of the diameter. And then we've had fairly rapid, fast fracture. Seems like a brittle fracture to me. And what we can conclude from this is that the cyclic load has been fairly high, maybe quite close to the ultimate strength, and that we can conclude from that this propagation hasn't gone that much, very far, so that we have only 25% of the diameter covered with the variating load with the fatigue propagation, and after that there hasn't been sufficient static strength, and the rest of the cross section has been broken with a brittle fracture. And also it means that probably there's a relatively small number of cycles to failure. Whereas in this bottom picture it's probably a screw, because I think we can see a side of the thread here. Also the initiation has been on the bottom side, but now we can see that fatigue crack propagation has lasted roughly to the half of the diameter, and only after then has happened the fast fracture. So we can conclude that this cyclic loading has been smaller in relation to the strength of the material than in the case A, which also means that there's probably higher number of cycles before failure than in the first case. So if you get the chance to look at the failed parts, fatigue failed or other failed parts, look at the cross section, you can make some judgments and conclusions out of it. It's very interesting to check those failed components if you're still alive, survive the failure. So, what happens to a material when it's under fatigue load? There is a main division that can be done between brittle and ductile. Brittle materials, they tend to have a fairly long initiation phase because they have high strength usually. Usually the brittle materials are the ones who have the high strength. So they resist longer for the crack initiation. But then, when the crack has been initiated, they usually have fairly high crack growth rate. So it's a fast propagation if it's just the loading keeps the same. So they have a fairly high notch sensitivity. Another type of material is ductile materials. And usually for these, because they have usually lower strength, the initiation phase is fairly short. So the first crack is formed quite rapidly. But as they are ductile, they have so-called low crack growth rate. So they tend to resist the growth of the crack better than the brittle materials. And then now if somebody asks that what is brittle and what is ductile, there is no clear division between those, but it's just a general idea of different materials. You can say, for example, that S355, that is ductile for sure. And if you have a bearing steel of 100 CR6, which has a yield strength of nearly 2000 megapascals, that's for sure brittle. And there's a transition phase in between those. And what is important to know that when you have a material that is brittle or is high strength, the total fatigue life is consisting mainly of the crack initiation. So with a high strength material, you should focus on how to prevent crack from initiating. Whereas if you have a ductile low knot sensitivity and maybe strain hardening materials. Strain hardening materials usually are favorable in fatigue because there's a plasticization in the crack tip. They tend to harden in that area, and that also further resists the crack growth. They are beneficial in that sense. So in these low knot sensitivity and strain hardening materials, you could sometimes utilize the crack propagation phase in the design. Sometimes, not always, but sometimes. Whereas if you have a brittle material, you should focus on to prevent the crack from initiating and not even thinking about how to calculate the remaining cycles to failure when the crack has already initiated. That is dangerous business. Here is a case example of a crack propagation. So here's a picture of rectangular hollow section corner. So the rectangular hollow section is a steel beam, like here in the right low picture. It's been cold formed, which means that there's a residual stress distribution over the wall thickness. And it was being detected that for this kind of beam, when it was put to a variable loading, there was always a crack that initiated from the inside, and then it developed pretty much straightforward to the neutral axis, and then it turned sideways. And a friend of mine, he made a dissertation of this, and he investigated what was the reason. And he found in his investigations that when the initiation starts, the crack starts to grow perpendicular to the major principal stress, as we described, mode 1. But then, when closing to the neutral axis of the cross section, the crack will hit into a compressive stress field, residual stresses from the cold forming of the tube. And that compressive stress distribution causes the crack to reorient, so it starts to turn sideways. And for some time it turns so that it goes almost in line with the neutral axis, where then it has passed the compressive stress distribution area, and after that it starts to grow again directly to the through. And the difficulty of this kind of breakage was, of course, that when the crack started from the inside corner, you could only discover this failure when it was completely through. So there was some booms of lifting equipment that were breaking in a way that there was a full breakage nearly all the length of the boom when the crack had hit the surface, and it was not being detected before that. So this shows how the crack can reorient itself in the conditions, like in this case the residual stresses. And the total life of fatigue loaded component can be expressed as a sum of the amount of the cycles, NP, that is needed to form the crack. So the cycles that are needed to initiate the crack, plus the cycles after the crack initiation that is required to ultimately fail the component. So the crack to grow until it completely fails. Sum of these is the total lifetime of a component. And as spoken before, the brittle materials, those ones who have a higher strength, their total lifetime NF is mainly dependent on this NP, so this crack initiation cycles. And MGE, the cycles required to grow the crack until failure, is fairly small. So the design must be based on extending NP as much as possible, and I would say that neglect the NG. Don't even try to utilize that for brittle materials. But if we have a ductile enough material, you might, some case, take use of the crack propagation also. Because they have low notch sensitivity, it means that the crack growing ratio is fairly moderate. There's a mistake in that. But what does it mean that it can be sometimes utilized? It means that there could be some conditions that prevent us from using the crack propagation phase. And another thing is that if you utilize that, you have to always use the fracture mechanics. If you don't know how to use it, then you don't apply it. But there's basically a possibility that if there is no other effects that might speed up the crack propagation, there could be a chance that you could utilize the crack growing phase also. That is usually done for components that are really weight critical. For example, these aircraft components usually, they are designed in a way that they also have some safety, even though there would be some crack. So most gain of this crack propagation phase you can gain with ductile materials, low notch sensitivity, and strain hardening materials. Tirkkonen, really, he has a hand raised. Do you have a question, or is it still, has it been forgotten?
I think I just have forgotten my hand up.
No problem. Just Jaakko asked that, doesn't it get tired?
I work out.
yeah, that's a good thing. Okay, now we learned something about how the material affects the fatigue life. But now, last time we spoke about the geometry effects. And this is something that is not dependent on the material. Because independent of the material, no matter is it ductile or brittle, this initiation is always considerably shorter for a member which has a notch. And the pure reason is that the local stress is so much higher. We learned some of the mechanical components that have the notch, like shaft with a journal or shaft with a groove in center, like here in the picture. But a similar case is, for example, in the weld toe, especially if there's an overlap or undercut. This is also a notch. And also there's a notch in this kind of single-sided fillet weld. There's a notch in the root side because there's no solid material in this area. So there's basically a readily made starting crack in the root of the weld. And what is the bad side of this kind of original crack in this side? What would you estimate? Why is it so disastrous?
Might be, it's hard to figure it out.
Yes. Jaakko probably had the same answer. You used the raised hand.
Yeah, and in the situation where the crack starts, the mode is already in one.
Yeah, that also.
So it's the worst case scenario when it starts there and the force is applied.
That's also true. If you have like a tensile or bending load in this vertical plate, it's already mode 1. That's also a good point. This is really disastrous. If the crack starts to propagate from here, and when it starts, you don't see it until it hits the surface. And then it's too late, usually. Okay. Now, these were some considerations that we should think when we do a fatigue life assessment. Next, we are moving on to how to do the assessment. I have divided these methods into 3 different categories. Somebody else might categorize them different, but I think this is fairly reasonable from the basic concept used. So first of them is the stress-based methods. So this means the methods that we base or where we utilize the Wöhler curve, the SN curve. Of course, we have to include the effect of the different mean stresses. When we learn that the mean stress could be 0, but it could be something else. And that we need to somehow include in the calculation. There are different ways to do it. Goodman, Smith and others, we will learn it later on. And these stress-based measures, they are the, so to say, the most traditional way of doing fatigue life assessment. And it is, for an engineer, I would say that 99% of the cases can be covered with this. It's very useful when you have a fairly high fatigue life. So the total number of cycles is roughly more than 100,000. And it's applicable when you don't have local yielding due to the notch. If you do have local yielding due to the notch, then it doesn't apply. You have to use the number 2 strain-based method. But usually we want to design the components in a way that even though there would be a notch, the stress at the notch would be below yield strength. So therefore these are applicable. And also it's only applicable when you do not have the initial crack, because these stress-based measures, they pretty much rely on the crack initiation and how to control the crack initiation. So if there already is a crack, they don't really apply. There's no method that you could include the existing initial crack in the assessment. And also it's useful when you don't specifically need to separate the crack growth area or the time needed for crack growth. So you don't need to calculate that precisely what is the actual exact amount of the numbers to failure. And 99% of the engineering cases can be covered by these. But there are also cases where you need something more. And second is the so-called strain-based methods, which means that where in stress-based methods we have this stress amplitude versus lifetime. In strain-based methods we have strain amplitude versus lifetime. So we don't refer to stress, we refer to strain amplitude. But otherwise, I would say roughly similar approach from the point of view of the lifetime curve. But then the equations are different. So they're used so-called Ramberg, Osgood, and Coffey-Manson relationships. And you should use these when you have total lifetime for the compound is relatively low, less than 100,000, and you have a local plasticization. Because the strain life method requires that you have the plasticization locally at the notch, and then you can apply it. If you don't have the local plasticization, it doesn't apply. And this is also something that you just need to know that it exists, and it is there. But we don't in this course learn how to use it. It would be a subject of complete course. And also a subject of complete course would be a fracture mechanics, which is then, I would say, the mother of all fatigue life assessment, in a way that this is something you can use pretty much for any number of cycles in any geometries. It will include both the initiation and the crack propagation. You can include the crack initiation phase as well, and you can also perform infinite lifetime calculation with the fracture mechanics. That is something we might maybe try at this course when we have enough time. It's not actually in my scope of the course, but if you're interested in, we could do later on maybe a small calculation tryout to how to use fracture mechanics for infinite lifetime calculation. It's not that difficult. But let's see how it goes with the other topics before the April. And that is also, of course, useful when you need more precise assessment for how long time or how many cycles it requires the existing crack to grow. And of course, it's the only option if you already have the initial crack over there, because then you can't use the stress-based method anyway. And what is important is that as an engineer, you would need to judge which is the method that needs to be applied. Even though you wouldn't be familiar with strain-based methods or fracture mechanics, you should know that if you face a problem that would clearly require strain-based methods or fracture mechanics, you should take the case to an engineer who is able to do it and not try to just force it with a stress-based method, because you will get disastrous results. And also it's good to know that for welded components, it's slightly or completely different story. Same principles apply, but there are different rules for those, because there are residual stresses, etc., what need to be taken into account. So if you want to focus on that more, please go to IIW, International Institute of Welding, recommendations for fatigue design of welded joint and components. But we don't cover that in this course. Okay, I think we are quite well on time. So now you've had quite a bunch of theory. So and later on we will learn how to calculate the fatigue life. But what is really important, if you don't anything else remember from this course, do remember this. So even though you don't know how to calculate the fatigue life, the exact number to failures, you should have knowledge about the general things or methods that you can use, or how to design the component against fatigue. What are the parameters that affect to the fatigue lifetime? And this can be generalized as three categories on the fatigue life improvement. First is the increasing local strength. Second one would be to reducing the local stress. And the third one is the preventing harmful ambient effects. And there are, of course, more detailed methods under these each. So how to concretely apply that. But all of them are basing into the fact that the fatigue crack initiation is a local event. As we saw in the microscope pictures, it's always a local, in a very small area where the highest stress is and where the initiation starts. It's a local event, and that is the area we need to affect. And now, a small group task, a quick group task, maybe 5 minutes. I will divide you into the 24 people over there, so maybe I will divide you into 6 groups. And your task is to, as a group, think how would you improve the fatigue strength of a connecting rod, meaning the piston rod here in this engine. And consider the ways how can you increase the local strength, how can you reduce the local stress, and how can you prevent harmful ambient effects to the component. And please go to this answer garden address, and there's a wall where you can write your answer. Just put any ideas that you get into your mind, and then if we have time we can briefly look at those together. If not, I will share it into the Moodle page. But now I will share you into 6 groups, and then you can start thinking and just decide first who is the secretary and writes them down. Thank you, Jaakko, you put the message to the chat, this link.
Is there an issue with the answer garden since I can only see our answer?
You need to reload the page. I think then you should also see the others.
Yeah, now I can see. Yeah.
Okay. I think everybody's back in the meeting now. So even though there was not that much time for you to do it, it seems that you got good ideas. I'll now briefly show you what the overall answers. So you will see the inputs from others if you reload the page. You only see your own if you just submit your own, but reloading the page will show you the others. But good ideas about this. I will put this as a picture into the Moodle, and now our time for today starts to be up, but for next time I would like you to recap from the Moodle lecture material, which I will put there shortly within 5 minutes. I will show here a couple of slides still, and I would like you to consider these topics. Consider these topics for next session. Are you seeing my screen now?
We see the PowerPoint, right?
Okay, good. You should. So here are some of the details which are under the main topics. So what does it mean that when you increase the local strength? What can you do? Also, what can you do about reducing local stress? And what can you do about preventing harmful ambient effects? And these 3 slides, I would say that they are the most important for today's lecture. So I will put the material into Moodle and read it carefully through for next time, because these are the things that you can, as a designer, you can do completely without doing any calculation. You don't need to know anything about the fatigue methods or how to apply Whirl equations or whatever. If you follow these general rules, you will end up into fairly good design against fatigue, even without any calculation. So therefore, it's very important for you to know. And by far, surely I will question these in the exam, so for you to know it. Okay, so now we are already a couple of minutes over time. So thank you for today, and I will shortly put the material into Moodle, and we will continue after 2